Okay, so in our last video, actually in class on Friday, we talked about the law of conservation of matter, which is that matter can never be created or destroyed. So there's also a law of conservation of energy. And since this unit is about matter and energy, we're going to be talking about both. So let's actually define conservation of energy, and we can use the same definition. So energy is never created or destroyed. But something that energy can do is transfer or change form. Okay. So let's talk about changing form first. It's important that you know that there are a lot of different types of energy, and they're broken down into two main categories: kinetic energy and potential energy. Kinetic energy is energy having to do with motion, and potential energy is stored energy. Okay, and then if we look a little bit closer, there are different types of kinetic energy and different types of potential energy depending on what the substance is. Okay, so we want to look at how one type of energy can change into a different type of energy. So in my first example, I have lighting a match. Before the match is lit, it has some amount of energy inside of it. It's able to do something, it's just not doing anything yet. So I want to pick from my potential energy list, what kind of energy does a match have stored inside of it before it's burning? It has chemical energy. And then once I light the match and it's burning, I want to think about what that chemical energy is turning into. So there's fire, right? There's light coming out of the match, and there's heat coming out of the match. Heat is another way of saying thermal energy, so I'll just write that over here. Okay, so the energy is not disappearing, it's just turning into a different type of energy. The total amount of energy is always the same. Okay, what about bouncing a ball? Okay, so as my ball is falling to the ground, it's moving, right? So that means the ball has mechanical energy to start with. My ball is falling to the ground. It's got mechanical energy. Once it hits the ground, we hear sound. Anytime there's friction, there's thermal energy involved, right? So we're changing the type of energy that the ball has. Okay, I want you guys to try number 3 on your own. So a solar flower dancing, those are those things that are, they're those little plastic things that you can put like by your window or in your windshield in your car. And when you sit them out in the sun, they move. So I want you to think about what kind of energy transformation would be happening there. Okay, so now we need to talk about heat, which is a type of energy versus temperature, because one definitely affects the other. They have a relationship, but they're not the same thing, and sometimes they're kind of used interchangeably when they shouldn't be. So as far as definition goes, heat is the total is important, kinetic energy of particles in a sample of matter, where temperature is the average kinetic energy of particles in a sample of matter. And I know it's like kind of like, well, what's the difference there? If you think about finding a total in math, right? You're taking the particles' speed and you're adding them up and you're finding the total. In total, how fast are all these particles moving? Where average, if you imagine a sample of matter, not every single particle in that sample is moving at the exact same speed. So you're taking the total and then you're dividing it by how many particles are actually there. So mathematically, when you're getting temperature versus heat, you're not calculating, you're not getting the same number, you're not measuring the same thing. Okay, so because temperature is just an average of the amount of energy the particles have, it's not an actual form of energy itself. Okay, because they're different things, they have different units. So temperature is going to be measured in joules. I'm sorry, I'm going crazy, guys. Temperature is measured in degrees Celsius or in Kelvin. And energy is measured in joules. So guys, this unit is good for any type of energy, not just heat, but in this unit, we're focusing on heat, and that will be our unit. How is it measured? So we have a thermometer. Okay. And then for heat has to be actually calculated. And there are 3 different formulas for calculating heat. And we're going to get to those in our next video. But I just want you to know that there's no instrument to measure how much heat something has. Measuring its temperature is not saying how much heat it has. Okay, so we're going to get to that in our next video. Okay, so what we want to look at now is this relationship. So this is actually a graph that you guys are going to have to understand. And what it shows is we have H2O starting in the solid phase down at negative 40 degrees Celsius. It's an ice cube, right? And as we add heat over time, the y-axis shows what happens to the temperature. So you would think, well, if I add heat to something, I'm going to make its temperature go up. And that's definitely true, except for in 2 spots. So what do you notice? And if you look at the particle diagrams here, that can help you. What do you notice is going on in these 2 spots that the temperature is not changing? You see the phase is changing. Here I have a solid and a liquid together. Here I have a liquid and a gas together. So when you add heat to something, you can make the temperature go up, or you can make the phase change. They both can't happen at the same time. One happens or the other happens. Okay, so you guys are going to be responsible for labeling these heating curves and talking about what's going on with energy during each section. Okay. So let's go to our next page. All right, so again, guys, now here's a blank heating curve. And the terms that you have to know associated with this are exothermic and endothermic. A heating curve is always endothermic. And I want you to remember endothermic means heat is entering. They both start with EN. But the word that you're going to see more often is absorbed. So this is what happens with temperature when we add heat to a substance. Okay, so you want to think about what phases we have first. So during A, we're below 0 degrees Celsius. So my coldest phase is my solid phase. What happens to a solid? What happens to ice if I continue to add heat to it? B is where melting occurs. And melting is solid to liquid. So I have 2 phases present. Once I'm done melting, C is my liquid phase. The temperature goes up and up and up. When I reach 100 degrees Celsius, my water is going to start to boil or vaporize. So again, I have another phase change, which is why my temperature is not changing. Liquid is turning into gas. And then finally, we're finished boiling. We have only gas. Now my temperature can continue to go up again. There's one more phase change, and it's actually when a solid skips straight to a gas. And that's called sublimation. And that's another endothermic phase change because energy needs to be absorbed to turn a solid to a gas. So an example of something that can do this is dry ice, which is frozen carbon dioxide. If you guys imagine going to the beach in the summertime, right? And there's always that guy that's walking around with an ice cream cooler. He's like selling ice cream. And what do you see when he takes the lid off of that ice cream cooler? you see all this steam, all this cold steam coming out, right? Carbon dioxide is not supposed to be a solid. It's a gas at STP. So to take carbon dioxide and to freeze it, you have to make it very, very cold. As soon as that dry ice is exposed to any amount of heat, it doesn't even have time to melt first. It's going to immediately turn into a gas. So that's what sublimation is. That's an example. Okay. Now, aside from being able to know my phases and my phase changes here, we also need to talk about what's happening with energy. So if you remember, the definition of temperature is the average kinetic energy of the particles. We can look at the y-axis as if it's labeled kinetic energy. So during sections A, B, C, and E, what's happening to temperature? It's going up. So what's happening to kinetic energy? It's going up. It's increasing. Now, only one type of energy is allowed to change at a time. So they're going to also ask you what's going on with potential energy in those areas. Well, if kinetic energy is already changing, then the potential energy has to be staying constant. They both can't change, just like temperature and phase can't change. It's one or the other. So that's important. Now for B and D, what's happening with temperature? It's staying constant. So what's happening with kinetic energy? It's staying constant. The heat is not making those particles move faster. What is the heat doing? It's making them spread out. Solid is turning into a liquid. Liquid is turning to a gas. Their position is changing. They're getting further apart. So potential energy is that stored energy that has to do with position. So if my particles are spreading out, my potential energy is increasing. Okay, so this is everything you have to know about a heating curve. Cooling curves are just the opposite. As time goes by, we see that temperature is decreasing because these are exothermic changes. Exothermic means heat is exiting the substance. But the word that you're going to see used more often is released. Heat's being released. Okay, so now guys, we're going backwards. We're starting off with my hottest phase. So we're starting off in the gas phase. What is it called when gas gets colder and it starts to turn into a liquid? We have condensing. Once we're done condensing, we're only in the liquid phase. We continue to remove heat. My temperature is going down, down, down. Eventually, my liquid is going to start turning into a solid, which is what we call freezing. And then finally, we're going to finish the freezing process. We're only going to have solid left. I can continue to remove heat, and the solid will just get colder and colder. The temperature will go down. There's also that jump, just like there is in the endothermic graph. When gas goes directly to solid, that's called deposition, meaning it didn't have time to condense first. It turned directly into a solid from the air. So an example of this is water. In the air, there's water vapor. There's some H2O gas floating around in the air. And typically when gas cools off, it turns into a liquid first. But I want you to imagine the air in your freezer. It's so cold in there that if water vapor is going to turn into anything, it's going to turn directly into a solid. So that's all the frost that's like on the inside of your freezer. That's water vapor from the air that deposited itself as a solid right onto your freezer walls. So that's another example of an exothermic phase change. So just like with the cooling curve, we can think of temperature as kinetic energy. So if we want to talk about what's going on with temperature during these sections, A, B, C, D, E, F, what's going on with temperature? It's going down. So kinetic energy is also going to go down. Same as the heating curve, guys, only one type of energy can change at a time. So if kinetic energy is changing here, then PE is not allowed to change. It's going to stay constant. If we look at B, C, and D, E, temperature is not changing because the phase is changing. So if temperature is not changing, then kinetic energy is not changing. What is changing is the phase. So the spacing of the particles are changing. Their potential energy is changing. As I go from gas to liquid, we're getting closer. Liquid to solid, we're getting closer. So what's happening to my potential energy? It is going down. Okay. So I'm going to just give you guys some practice questions with heating and cooling curves, and we'll get into a little bit more math and calculating heat in our next video. Okay, have a good day, guys.